Okay, so in this example, we're given the vapor pressure curves for carbon disulfide and nitromethane, the one in red and one in blue, and we asked some questions about those two curves. The first one says, what are the approximate vapor pressures of carbon sulfide and nitromethane at 40 degrees Celsius? So basically what we go ahead and we do is we draw a line here at 40 degrees Celsius, and we read off where they intersect the graph. So for the nitromethane, it's 100 millimeter mercury, or the exact value is apparently 90, and for the carbon disulfide, it is 600. So um, we can write that down. So the vapor pressure for carbon disulfide at 40 degrees Celsius is equal to 600 millimeter mercury. And the vapor pressure for CH3NO2 at 40 degrees Celsius is equal to approximately 90 millimeter mercury. Okay. Next question. What type of intermolecular forces exist in the liquid phase of each compound? Now, carbon disulfide, if you draw the Lewis structure, you will see is a linear molecule. It resembles CO2 versus the interesting thing about the methane, what do you call this thing, nitromethane, keep on forgetting it, I don't know why, is that technically has this kind of resonance structure. So I'm going to draw its resonance structure where it has O, O, and then has this balance between the oxygens to carry the charges. But in principle, how it actually works is this NO there's a negative charge on the oxygen, and of course the nitrogen carries a positive charge. But you draw that in the resonance where the nitrogen is positive and there's a negative charge. Negative charge here. Anyway, so that's the point. We need to analyze these structures. So SCS is non-polar. Therefore, the only forces that we can have are London dispersion forces. The other option here is polar. So this means we'll have London dispersion forces because all molecules have them, but also dipole-dipole forces. Right, there's no hydrogen bonding, so there's none of those, and no iron dipole or other kind of weird things. So those are the molecular forces present. See, what is the normal boiling point of CS2? So how do you check normal boiling point? You go to 760 millimeter mercury or 760 torr, and you read off at what temperature is that. And I mean, it's about roughly what you do. So for your normal boiling points, TBP is at when your vapor pressure is equal to 760 millimeter mercury, 1 atmosphere. So your boiling point of CS2 is equal to roughly 48 degrees Celsius, if you go and read it off the graph there. And your boiling point of the nitromethane is CH3NO2 is roughly 100 degrees Celsius. And actually, if you compare that to the experimental boiling points, this one is, or the ones that you can get on Google, this one is 46.5 degrees C, and this one is 100 degrees C. So the graph is correct. By the way, the graph is constructed from experimental data, but we might struggle to see it exactly here. So the point, the teaching thing that we want to get to is this, that you know that the normal boiling point of a substance is defined at 760 millimeter mercury. Okay. Question D. At what temperature does CS2 have a vapor pressure of 600 millimeter mercury? So a closed container, where does that happen? And we saw that, well, I mean, that's around about at 40 degrees Celsius. So it's just the same question as A, just posed the opposite way around. And then question E. At what temperature does nitromethane have a vapor pressure of 600 millimeter mercury? And again, we can just extend the 600 millimeter line here. We can see it's roughly at 95 degrees Celsius. Why? Extending this line here at 600 millimeter, draw it down here. It's roughly 95 degrees Celsius. Not exact. The point is how to read the graph. So if you have an exact graph and you can look on Excel or whatever, you can do it precisely. Yeah. All right. So thank you for watching. I hope you're able to interpret vapor pressure diagrams now and you're able to read them well. All right.